So the first question that we're going to study is, for a given vector space, what is the minimum number of vectors whose span equals that vector space? What's the minimum size of a set of generators? Now, there are two natural algorithmic strategies that you might try to find a minimum size set of generators. Here's one. I call it the GROW algorithm. Given a vector space, initialize your set to the empty set and repeat, as long as it's possible, choose a vector in the vector space that's not already spanned by the vectors in S, and add that vector to S. Repeat that until there are no longer any vectors in the vector space that are outside the span of S. At that point, you've got a set S that spans the given vector space. The question is, does this really give you the smallest generating set for the vector space V? Another question that we'll have to get to is, can this algorithm be made to stop? Does it ever terminate? Here's an alternative approach. I call it the shrink algorithm. Given a vector space, it initializes S to some finite set of vectors that spans the vector space, and then repeats, as long as possible, find a vector already in S such that the span of the set of vectors obtained by removing the vector from S is the same. It's still the vector space. And then just remove the vector. So we're shrinking down the set S. The algorithm stops at the point when removing a vector from S would result in not spanning the original vector space. So at the point that the algorithm terminates, if it terminates, the span of S is the vector space V. The question is this set of generators a smallest possible set of generators for the vector space? There's an additional question of how we do the initialization. We've given two algorithms, the GROW algorithm and the shrink algorithm, for finding a set of generators. Is it obvious that each of these algorithms finds the smallest set of generators? Let's look at examples from a problem in graphs. So here's a graph. The points are called nodes or vertices, and the links are called edges. Each edge has two endpoints. So for example, this edge's endpoints are these two nodes. The two endpoints of an edge are called neighbors. Now, a dominating set in a graph is a set S of nodes such that every node is either an S or is a neighbor of a node in S. So, for example, the set of nodes I've circled here is a dominating set. Our goal is to find a smallest dominating set in a graph. And here's one possible algorithm, the GROW algorithm. You initialize the set S to be the empty set, and while S is not a dominating set, we add a node to S. So we might start by adding, say, this node. It's not a dominating set yet, so we might choose to add, say, this node. At this point, we've got a dominating set. Every node is either in the set or a neighbor of a node in the set, so we can stop. But did this algorithm give us a minimum size dominating set? It turns out that no, we could have gotten a much smaller dominating set consisting, say, just of this node. So in this case, this greedy algorithm, the GROW algorithm, came up with the wrong answer. It didn't come up with the smallest solution. An alternative is the shrink algorithm, which initializes S to be the set of all nodes and takes away nodes as long as taking them away leaves you with a dominating set. Similarly, this algorithm can also fail to find a smallest dominating set. So algorithms like GROW and shrink don't always find you the smallest solution.